Okay, listen to this, because this idea completely changes how we look at building software. Don't try to find the best design in software architecture. Instead, strive for the least worst combination of trade-offs. If you've ever thought that software architecture is about hunting down that one perfect, flawless solution, well, I'm here to tell you that it's actually about something much more realistic. It's really all about managing the messy realities of complex trade-offs. Often, the absolute best design an architect can possibly create is simply the least worst collection of compromises.
Welcome to today's Explainer. We are going to completely demystify the foundation of software systems. We're popping the hood to see how massive digital products are actually structured, why certain critical decisions are made, and how those specific choices determine whether an application succeeds or completely fails under pressure. So here is our roadmap for today. We'll start with number 1, beyond the software blueprint. Then 2, components, connectors, and interfaces. 3, the crucial ilities. 4, making architectural decisions. 5, the stakeholder translation. And finally, 6, monolithic versus distributed architectures. All right, diving into section 1, beyond the software blueprint. To really get this, we need to move past a very common misconception right out of the gate. People so often refer to software architecture as simply the static blueprint of a system. But software isn't a building. It's dynamic, it's constantly evolving, and it is highly reactive to change. So, the crucial point here is understanding the firm boundary between architecture and implementation. In the industry, this is actually summarized by the second law of software architecture, which states that why is more important than how. Implementation, we're talking the code, the user interface, the class diagrams, that is the how. Architecture, on the other hand, is the why. Think of implementation as the actual bricks and mortar used to build a structure, while the architecture is the big picture decision of why we're building a hospital instead of a shopping mall. An architect can look at a system and figure out how it works pretty quickly, but without knowing the architecture, they won't have a clue why certain structural choices and trade-offs were made in the first place. Picture software architecture like a giant container holding up the entire system. At the very bottom, you have heavy pillars representing the overall structure or style of the system, but that container relies on 3 other dynamic elements to hold everything together. You have the architecture characteristics representing operational needs, the architecture decisions acting as the hard rules and constraints, and finally, the design principles that guide the development teams day to day. It is a living, breathing ecosystem, absolutely not a static drawing. Moving right along to section 2, components, connectors, and interfaces. Let's see how this translates into the physical anatomy of the architecture. Because before an architect even worries about code, they have to think about these foundational pieces. Architects partition a system using what we call components. These are the physical manifestation of modules. Basically, they are the deployable units of code, and they come in a few different varieties. For example, a component might be a dedicated payment processing module, or a massive user authentication subsystem. Maybe an event processor handling live data streams, or even a standalone distributed service interacting with its own private database. The architect is the one who decides exactly how to chunk the system into these manageable pieces. But obviously, these components don't just sit in isolation. They have to talk to each other. And that brings us to connectors and interfaces. Interfaces define the vital communication contracts. They dictate exactly how these independent, chunky components are accessed and orchestrated. Whether it's happening through a gateway, an integration hub, or an API proxy, these interfaces represent the coupling points of your entire system. Think of it literally like a power outlet. As long as that plug interface stays exactly the same, you can swap out a reading lamp for a toaster, and you don't have to rewire your entire house to make it work. Okay, section 3, the crucial abilities. Now that we have our physical components and our interfaces sorted, we need to look at the operational realities they live in. This is a super fascinating area, known in the industry as the abilities. We're talking about terms like availability, scalability, elasticity, testability. These are your architecture characteristics. What's absolutely crucial to grasp here is that these define the success criteria of a system, but they are entirely separate from the system's actual domain functionality. Let me put it this way. You might have coded the most beautiful, seamless e-commerce checkout feature in the world, but if the system lacks the architecture characteristic of availability during the Black Friday rush, it crashes and literally no one can buy anything. Architecture directly influences these make or break success factors. If you anticipate massive user growth, you architect for scalability. If a system failure means millions of dollars lost per minute, you architect for fault tolerance. But here's the catch.
Every single one of these abilities adds massive complexity to the design. A critical job for the architect is actually choosing the fewest architecture characteristics necessary. You can't just try to support all of them, because every single one requires a massive trade-off in time, cost, or system complexity. Which naturally leads us right into Section 4, making architectural decisions. This is where we shift to the human element, specifically how architects actually establish the rules and constraints that developers have to follow. Here is a massive, everyday challenge in software engineering. Picture this. It's 2 years from now. A brand new developer joins your team, and they look at the code base. They can easily see what was built, but how on earth do we preserve the reasoning behind those structural choices? How do they know the specific trade-offs that were made so they don't accidentally undo a critical constraint and break the system? Well, the industry standard solution here is actually brilliant because it's so incredibly simple. They're called architecture decision records, or ADRs. It's literally just a short text file, maybe 1 or 2 pages long. It uses an affirmative voice, something like, "We will use asynchronous messaging between services." And crucially, it captures the complete justification for that decision right there. For instance, it documents exactly why the team chose AWS over Azure back in 2022. It places the emphasis entirely on the why, serving as a permanent, searchable historical record of the trade-offs accepted at that exact moment in time. Now, of course, human decision-making isn't always perfect. Architects often fall into what we call anti-patterns. These are repeatable behaviors that produce predictably negative results. Covering your assets is when architects are just too paralyzed by fear to actually make a firm choice. Then there's Groundhog Day, which is the agonizing reality where a team debates the exact same architectural decision every single Tuesday because nothing was ever written down in an ADR. And my personal favorite, email-driven architecture. This is the nightmare scenario where critical system rules are buried deep in a forgotten email chain from 3 years ago, rather than being centralized where everyone can actually see them. All right, Section 5, the stakeholder translation. Overcoming those anti-patterns requires crystal clear communication, which brings us to the architect's role as a translator. They are the ones bridging the massive gap between highly technical metrics and big-picture business goals. There's a real lost in translation problem that happens in tech. Business stakeholders don't walk into a room and talk about system elasticity. They talk about user satisfaction or gaining a competitive advantage. The architect has to take that business domain language and translate it into technical architecture characteristics. If the business is planning mergers and acquisitions, the architect knows, okay, we must prioritize interoperability so we can integrate new systems. If the business wants a competitive advantage by releasing features rapidly, the architect knows they must design for agility and deployability. It's this continuous high-stakes translation from business language to structural code constraints. And finally, Section 6, monolithic versus distributed architectures. Let's look at the absolute highest level architectural style decision an architect has to make. This is a choice that happens before a single line of code is even written. First up is the monolithic approach. In a monolithic architecture, the system is deployed as a single, massive unit. Think of a startup pushing out its very first MVP application. Even if the code is organized neatly into modular blocks or layers internally, the whole shebang gets bundled together and deployed to a single shared database. It is generally much simpler to build and test initially, but it forces every single part of the system to share the exact same operational characteristics. But compare that to a distributed architecture, like the microservices used by tech giants like Netflix or Uber. Here, the system is completely broken apart. Services run in their own distinct address spaces and communicate over a network. This gives you incredible flexibility. One specific service can scale up independently of the others if it gets a spike in traffic. But remember our theme for today? Everything is a trade-off. Distributed systems introduce massive complexity when it comes to network reliability, data consistency, and distributed transactions. Basically, you gain amazing agility, but you absolutely pay for it in complexity. And that brings us full circle. Software architecture isn't about finding perfection. It's about deliberately choosing which problems you are willing to live with in order to get the benefits you absolutely need. So I'll leave you with this. The next time you open up that app you use every single day, whether it's lightning fast but occasionally drops a connection, or it's incredibly reliable but painfully slow to update, ask yourself, what architectural trade-offs did they choose to make behind the scenes? Thanks for joining me for this explainer, and keep questioning the why behind the technology you rely on every day.